Hi, I'm Babak Moaveni, an Associate Professor of Civil and Environmental Engineering at Tufts University. The title of my presentation is Integration of Sensor Data with Physics-Based Model for Performance Assessment of Civil Structures. Structural health monitoring refers to the process of assessing the state of health of structural systems using measurements. Usually we categorize them into global methods, which deal with large structures and sparse measurements, and refer those methods to SHM, as compared to local methods, which we also refer to them as non-destructive evaluation or NDE methods, which deal with dense measurements and localized damage using wave propagation mostly, acoustic emission, ultrasonic methods. There are many challenges in application of SHM methods to large-scale structures such as civil structures, which is the concern of this presentation. One of the more common methods for SHM are vibration-based methods, and among the vibration-based methods, model updating has received more attention in recent years. However, this method is mostly applied in deterministic manner using linear system theories. In this presentation, I will give a brief introduction to model updating, and then I will show several applications to large-scale civil structures. Three of them are concrete buildings with masonry infills, and one of them is a footbridge at Tufts campus. The focus here is probabilistic model updating. I will not go over the nonlinear methods or ongoing projects in the interest of time. The process of structural health monitoring include collection of data, which is the first step, and we mostly deal with ambient vibration measurements. Second step would be identification, which is an inverse process, which in this case we use model updating. Next step would be performance assessment. We use the predicted response time history as a metric for assessment of the performance, and we do not go into decision making in this presentation. Model updating is the process of tuning parameters of model M shown below, so the data from the model match those measured. This can be done through an optimization in a deterministic approach or through sampling in a probabilistic approach. The challenges for vibration-based methods such as model updating is that they are sensitive to ambient and environmental conditions such as loading and air temperature. Therefore, it's good to have specialized probabilistic methods that we can account for these sources of uncertainty explicitly, which is the topic of this presentation. The other challenge which we will not address in this presentation is that most of these methods are linear methods relying on low amplitude vibrations, while some of the changes in dynamic properties may not be visible in the low amplitude vibration data. The probabilistic methods can be categorized into Bayesian or frequentist approaches. The Bayesian approaches basically measure probability as a degree of belief. They assume that all of the uncertainties are epistemic. When you collect more data, this uncertainty will be reduced. On the other hand, frequentists consider certain types of uncertainties are very complex and we cannot treat them as epistemic. Therefore, they believe probability measures a proportion of outcomes. The example of flipping a coin is frequentist approach. You get a bag of coins, you just throw the bag on the ground, count the heads and tails. The Bayesian approach is that you flip a coin, you give me more information about the force that you flip, the ground information, the height, and I can give you more confidence level on the outcome. The first application I'm going to discuss here is a two-story building in El Centro, California. As you can see in the timeline here, the building went through 4 major earthquakes, and after the last one, it was tagged as unsafe and scheduled for demolition. Through an NSF grant with my colleague, Professor Stavridis at University at Buffalo, we performed certain tests on this building and collected vibration measurements. The building was instrumented with triaxial accelerometers. As you can see, there are 5 of those at each floor on the floor plan. We had a shaker at the northwest side, and we also had LiDAR measurements that a colleague from University of Nebraska, Professor Woods, and his team, they collected the LiDAR measurements. We had more than 8 hours of ambient measurements. What we use here is 300 minutes at the reference date and 107 minutes at the damage states. And we broke into windows of 10-minute data. So that gives us 30 sets of data for reference and 10 sets of data for damage state. But what is the induced damage on the building? The building was already severely damaged. We're not talking about that damage identification. We can work on that too, but the focus is to be able to estimate the damage that we induced through wall removals and shaking of the building. So if you can see in the bottom plot on the right-hand side, there are 4 walls that they are marked with red. Those 4 walls were removed using a forklift as it is shown on the left plot. And also we used a large shaker. It's an eccentric mass shaker from Nice at UCLA that we put on the second floor northwest side, and the shaking was strong enough to cause some additional damage. This slide shows the system identification results, mainly the natural frequencies and damping ratios, as well as the mode shapes. Note that the table shows the statistical information of the identified parameters. In the reference state, we had 30 datasets. Each dataset gives me 1 set of modal parameters. The first number shows me the mean value, and the second number shows me the standard deviation. The natural frequency of the first mode was identified as 2.26 Hz with 0.01 Hz standard deviation. After the induced damage, the modal frequency was reduced to 1.96. You can see that the standard deviation of the natural frequencies are very small across different data sets, while the dampings show larger deviation. The figure in the bottom right shows the top view of the building. For the 2 modes, you can see the roof has most of the motion, while the ground floor and the second floor don't move much, with blue and green. And the compass plots show that the mode shapes are identified as classically damped, as the arrows are aligned. LiDAR or point clouds measurements were also made before and after damage was induced to the building. We used LiDAR measurements to get the exact geometry measurements of the building and also for crack detection. In the bottom right plot, you can see that the cracks or surface defects were detected automatically and marked with red over black. This table shows the surface defect percentage identified from LiDAR or point cloud measurements. So the surface defect percentage is a measure of how much cracks we see in the area of the walls. And you can see that in the second level walls, for example, at the reference state, we already have significant damage. And at the damage state, that surface defect percentage increases. And what we are interested in is in the difference between the two stages of damage. And that contributes to the induced damage only by the shaker. And you can see most of the induced damage is observed in the west wall in the second floor and north wall in the second floor. An initial finite element model of the building was created in SAP 2000 structural analysis software, as well as another one in OpenSeas, which was nonlinear, but we only considered it in the linear range. The geometry of the structure was based on the LiDAR measurements, and material properties were obtained from coupon testing. We considered two models. One was referring to the initial assumptions that we made before visiting the building, and we called it untuned. And the other one was called tuned, which we manually changed the stiffness of walls based on in situ damage observations. And you can see the modal properties of the untuned and tuned models compared to the identified values. This slide shows the damage identification process through model updating. Basically, in the reference state, we have measurements. We calibrate our finite element model to represent the measured data in the reference state, and we call it a reference model, different from the initial model. And we have the data from damage state, and the calibrated model to represent those data is called damaged model. And the change in the stiffness parameters of those two models refer to the structural damage as loss of stiffness. In this application, we considered 10 updating parameters, which are all corresponding to stiffness of different components. So the first 4 parameters are stiffness of the walls, exterior walls on the first story, theta 1 being on the west side, 2 on the east side, 3 north, and 4 south. 5 to 8 correspond to similar directions in the second story. 9 and 10 are only used for the reference model and correspond to slabs and RC columns and basement walls, respectively. This figure shows the damage identification results as loss of stiffness for different components. Theta equal to 1 corresponds to no damage, and theta equal to 0 corresponds to 100% damage. Note that we have 30 reference models and 10 damage models, so we have different combination of damage identification results. The box plots correspond to the 10 values, and the 4 different colors, shades of green, correspond to different reference models, where the first one is the average, the one with the lowest modal parameters or natural frequencies, medium, and high among the 30. The red bars are what we expect to see just based on wall removals. So in thetas 1 through 4, no wall is removed in those directions. Theta 5 is the one that we removed 4 of the 8 walls. Theta 8, we removed one of the smaller walls out of 4. So we expect maybe a little less than 25% loss of stiffness. And you can see the identified damage is corresponding, except that damage is overestimated for theta 5 and 7 and a little underestimated for 8. We expected underestimation for 8, but the overestimation of 5 correspond to the damage due to shaking. 5 and 7 correspond to north and west walls, which is exactly closest to the location of the shaker. So the extra damage is induced by the shaker and is consistent with north and west of the second floor, which was observed by LiDAR measurements, which is a good consistency between LiDAR and vibration measurements. In summary, overall, the damage identification results are accurate with small variability and represent the expected damage. There are some overestimation of damage, which we expect them to be real and caused by shaking, and this is consistent with LiDAR. The small variability that I mentioned correspond to the variability across different data sets, which are all ambient vibration. However, if we use forced vibration measurements, the variability would be very significant. So it is recommended when we use linear model updating, we use similar amplitude data for both reference and damage states. The next application is also on a reinforced concrete building with masonry infills. This building is a 4-story school in Nepal, and the measurements are post-Gorkha earthquake. The main shock of the 2015 Gorkha earthquake happened on April 25 of 2015 with a magnitude of 7.8. The epicenter was close to Kathmandu, the capital of Nepal, and the main shock was followed by 400 aftershocks with magnitude of greater than 4.0. One of these aftershocks was in 12 of May with a magnitude of 7.3. The series of main shock and aftershocks caused more than 500,000 buildings to be damaged beyond repair and caused a lot of fatalities and injuries. Our team visited Nepal in June of 2015 and a couple more visits that I only focus on this visit and one school building that I mentioned. The considered school building is located in Sanghu, close to Kathmandu, and is a 4-story reinforced concrete frame with masonry infills. You can see the plan of the building in the view and the location of sensors on each floor. So the plan view of this school building is slightly irregular with the staircase on the left side, and you see the infills are not also evenly distributed. That caused a little bit of torsion to begin with for the response, but what we observed, and this was a common theme in Nepal, was that little bit of irregularity will cause significant damage on one side of the building. This is similar to what we saw in this building. You can see the walls that are are marked with red are severely damaged, while the walls with green, which are on the left-hand side, are not damaged at all. So we concluded that there was significant torsional motion due to the earthquake. This slide shows the response of the building to the main shock and the largest aftershock. You can see the two input excitations are following one another on both north-south and east-west. So this is a biaxial, bidirectional excitation. And you can see the plan view of the building, and the motion verifies our assumption of torsional motion, much larger deformation on the south side of the building. This is a nonlinear model which was calibrated. It's outside the scope of this presentation and was prepared by our colleagues at University at Buffalo. The initial model for the purpose of model updating was developed in OpenSeas, and we only cared about the linear portion of the model or the initial tangent stiffness. The frame elements were used for reinforced concrete frame, and strut elements were used for the infills. You can see the drawing of the finite element model on the right hand side, and in the left hand side it shows the elements we removed from the finite element model from the inspection of the building. The walls that they have crosses on them, it means we expected no remaining capacity or stiffness, so for the columns that they are crossed out. Here we can see a comparison between the finite element model parameters with those identified from measurements. We can see that the identified natural frequencies are close to those of the model, except for the second mode, which has 25% error, and the Mach values, which compare the mode shape vectors, are also pretty high, close to 1. In this study, we performed model updating of the initial model to match the identified model parameters. The considered objective function is the difference between natural frequencies and mode shapes, as well as a regularization term in the deterministic approach, and corresponding to that, we considered a similar prior and similar likelihood function. So we performed both deterministic and Bayesian model updating. And in the updating approach, we calibrated 9 modeling parameters, which are all stiffness values. The value of 1 corresponds to unchanged stiffness, value of 0 means completely damaged. You can see also visual of those parameters. For the first story, for example, theta 2 and theta 4 are the walls in the long direction or north-south direction, which we did not consider any reduction in our initial model. So we expect the theta 2 and theta 4 to get reduced because of the cracks we observed, but we didn't implement in the model. This table summarizes the model updating results. Again, the theta values are stiffness ratios. A ratio of 1 means no change, a smaller number means reduction, larger number means increase from the initial assumed value. Note that we did not have any measurement before the earthquakes. So this is just based on the assumption of the initial model and compared to that. So as I mentioned in the previous slide, theta 2 and theta 4 are the elements that we suspected there is damage. We observed some cracks, but they were not as much as the other ones that we completely removed them. You can see that both deterministic results and Bayesian results provide significant loss of stiffness in theta 2 and theta 4, with the smallest uncertainty for these two damaged elements. The uncertainties in the Bayesian values are in parentheses. In the Bayesian approach, a sampling method was used to estimate the posterior distribution of updating parameters. The top plot shows an example of 2 parameter samples, theta 4 and theta 5, one with lower uncertainty, one with higher uncertainty. Theta 4, you can see that there is a large reduction. The average value is around 0.3, and the samples are very tight around 0.3. Theta 5 corresponds to a wall in the higher floors, which is not as sensitive, therefore has larger uncertainty. The average value seems to be around 0.85, and the uncertainty, as you can see, is much larger than that of theta 4. The bottom plot shows how the samples, this is a metropolis hasting or a random walk, evolve as the colors change. So they start with blue color. I believe that's the first 10,000 or 5,000 samples, and then it goes to green, and then the last 10,000 samples are red. So you can see they tend to converge. And the two axes are two different parameters. For example, in the subplot on the left side, you can see a negative correlation between theta 1 and theta 2. And in the bottom right plot, you can see that there is no correlation, but there is much smaller uncertainty for theta 4, as we mentioned before, compared to theta 3. In summary, we were successful to do performance assessment of the buildings we visited using just post-earthquake ambient measurements, of course, combined with accurate initial finite element models. In the specific application I showed you, we found that the most probable values of the estimated model parameters are very consistent with those obtained from a deterministic optimization. We found the results to be sensitive to the choices of updating model parameters, residuals, and most importantly, the prior information or the regularization term. We were happy to see that the damaged elements in the first floor were identified with the most confidence level or lowest uncertainty. And these damaged elements match what we saw in the actual building. We also performed a second case of identification, which was actually the first case that we did without removing the damaged elements. In that case, we had more updating parameters. It was more computationally expensive, but the updating results clearly indicated that there is no remaining stiffness in the elements that we already removed. In this section, I will review a hierarchical Bayesian model updating approach where we can consider different sources of uncertainty in the updating scheme. The motivation for the proposed hierarchical Bayesian model updating is that the sources of uncertainty, specifically for civil infrastructure, can be categorized into two. One of them are parameter estimation uncertainty, such as measurement noise or identification error, which are considered epistemic. You add more data, these sources of uncertainty always reduce, and you can get up to zero variability because of these sources. Then you have the second source of uncertainty, which is the actual valid variation of the physical properties of the system, such as changes in mass. For example, in a building or a bridge, due to traffic or occupancy, you have some changes in mass. Or because of the temperature change, you have stiffness changing. Or the effective stiffness changes due to the ambient loading. For example, the plot here at the bottom shows change of temperature, change of natural frequency versus temperature. You can see at the 0 Celsius, which is the freezing point, the natural frequency of this mode starts to increase. This is for a footbridge on campus at Tufts. So there is a physical phenomena that causes this change. This is not just randomness. This is not due to noise. And if you add more data, the estimation uncertainty shouldn't go to zero. You should be able to observe this variability. And you can see the histogram of the natural frequency due to this phenomena. So in the proposed hierarchical Bayesian model updating, we estimate parameters of our stiffness, not the stiffness itself, the statistical properties of it. So we assume stiffness has an underlying variability which can be characterized by For example, a normal distribution. I don't care about the optimal value of theta, which is the stiffness. I care about the optimal value of statistical properties of theta, or mean of theta and variance of theta. As it's shown in the diagram below, I want to estimate mu of theta and sigma square of theta. And then the remaining uncertainties can be categorized as sigma e or modeling errors. So as I mentioned, we assume theta, which is our stiffness parameter, for example, follows a known distribution such as normal, log normal, and we can change that as we perform the updating, with unknown parameters mu and sigma, which are our hyperparameters, and we are interested to update. You can write the base formula. It has the likelihood, prior, as well as hyper-prior terms. And the error function, as previous studies, are the difference between eigenproperties or natural frequencies and mode shapes. This simple 3 degree of freedom numerical example will show the application of hierarchical Bayesian model updating. Consider that the stiffness of different stories are theta 1, theta 2, and theta 3, and do have an actual variability, which is characterized by a normal distribution with mean 2100 for the first story, 1050, second story, 1020 in the third story. That gives me distributions for the measurements of natural frequencies as shown in the bottom plot. We simulated 400 sets of modal parameters and performed hierarchical Bayesian model updating. Here you can see the results for increasing number of measurements. Different lines correspond to 5, 20, 50, and 400 data points. And the line that has a dot going through it is the exact underlying distribution. You can see that after having once we have more than 5 data points, the distributions tend to converge to the exact values. However, note that while you don't see much difference here between 50 and 400, because these are the most likely values of mean and standard deviation for these plots used, but the estimation uncertainty of mu hat and sigma hat reduces as we increase the data, which is not shown here. This slide shows the results of the same problem of model updating when we don't use hierarchical Bayesian, but a classical Bayesian approach. In other words, the classical Bayesian model updating does not consider an underlying distribution for model parameters. It does not consider inherent variability. Therefore, as you increase the number of data points from 5 to 50 to 400, the uncertainty or estimation uncertainty decreases, which means how certain the method is that 2000, 1000, and 1000 are the best choices for theta 1, theta 2, and theta 3 respectively, which is suitable for many cases of application. However, it is not suitable when we want to estimate the uncertainty or variability corresponding to the underlying or actual physics-based variability of updating parameters. In summary, the hierarchical framework is suitable when there is inherent or underlying uncertainties for model updating parameters, and the results are consistent with those from frequentist approach. The next considered application case study is a 10-story building in Utica, upstate New York, which is a concrete building with masonry infills. Here we can see a plan of the building and the location of accelerometers on every floor. We have 2 triaxial accelerometers on every floor at 2 corners, and we have more than 300 data sets available from ambient measurements. For the sake of model updating here, we used only 50 sets of model parameters, and each set includes natural frequencies and mode shapes of the first 3 modes. A hierarchical Bayesian model updating approach is implemented here for model updating, and in this application, the error function is assumed to be the difference between eigenvalues and mode shapes of the model and those from the data. And we have 50 sets of data. One novelty in this application is that we assume that the error function is not necessarily zero mean. So we also update the mean, and we investigate the effect of the bias here in the error function on the accuracy of response predictions. An initial finite element model of the building was created in SAP 2000 using strut elements for infills, frame elements for beams and columns, and shell elements for slabs. The model was reduced to a reduced order model for the hierarchical Bayesian model updating. The natural frequencies and mode shapes of the first 3 identified modes are shown here. As you can see, the first mode is mainly a translational mode, while the second and third modes are torsional. In this table, we can see a comparison of the modal parameters from the finite element model and those identified. Note that the mean value of the identified values over more than 300 datasets is only reported here. You can see that the initial model matches very accurately the mean of the identified values, and that's because the initial model was mildly tuned to match the identified results. However, the tuning has not been done through an optimization process. The hierarchical Bayesian finite element model updating approach is implemented here to calibrate 2 structural parameters, which are the effective stiffness of concrete walls as theta1 and that of concrete slabs as theta2. And that's it. We have 2 structural updating parameters. However, we update the parameters of these 2 Young's moduli as mean and covariance matrices in the hierarchical approach, as well as the modeling error properties. One novelty in this application is that we do not necessarily consider the error functions to be zero mean. As you can see, we consider 3 cases of calibration. In the first case, we consider zero mean error functions. In the second case, just one of the error functions, which we observed clear bias, and that is for the third modal frequency, is also updated, non-zero mean. Case 3, 2 of the modal frequencies are considered non-zero. Therefore, mu of omega 2 and mu of omega 3 are updated. The calibrated model is used to probabilistically predict the response of the structure. The response can be the time history response due to a known input excitation, or it can be modal properties. Here we are looking at the modal frequencies for the first 3 modes. The prediction will have two parts. The first part would be considering the variability in the updated structural parameters, theta. Therefore, the variability of theta comes from mu of theta and covariance matrix. And the second part would be coming from the modeling error, which explicitly account for the bias or the estimated mean of the error function. This figure compares the probabilistic prediction of natural frequencies using the calibrated model and those measured from the data. Note that we use more data sets for this plot than those used for model updating. 302 used here, 50 were used for model updating. The identified or measured values are black dots. The predictions are gray circles. You can see that the graphs have two axes, F1 versus F2 on top and F1 versus F3 at bottom. So you can see clouds of points. Each of the columns correspond to one case of model updating. The first case or case 1, no bias considered. Case 2, only error function for the third modal frequency is considered to have bias and the mean of that error function is updated. Case 3, the bias for error function for natural frequencies of modes 2 and 3 are updated. Now you can see that the first mode predictions show not much bias to begin with. So if you look along F1, the black dots and gray dots, they pretty much have centers similar to each other. However, in the other directions, along F2 and F3, you can see a clear bias, differences in the centers of the two clouds. Overall, the 95 percentile or 99 percentile, which is plotted here, covers the data pretty accurately, however, is not tight enough in case 1. In case 2, we add the bias explicitly in the estimation, and you can see that the bottom plot in case 2 gets much tighter because we consider the bias and therefore the variance doesn't have to account for that or compensate for that. And the last case we consider for both modes 2 and 3, and that one has the tightest fit. So that estimation is very, very tight. You can see that the uncertainties due to the inherent variability of structural parameter and the bias as well as variance of the modeling errors considered and provide a very tight estimate. In summary, if we want to have reasonable predictions and realistic confidence bounds on our predictions, we need to consider both model parameter uncertainties through a hierarchical approach, as well as the modeling errors, which are as important or sometimes more important than the uncertainty of model parameters. If we consider a more complete error function and update those parameters, for example, in the case that we showed, if we estimate the bias or the mean of the error, in addition to the variance, you will have a tighter fit to the data. However, in the last bulletin, I say that if we do that, there is a danger to extrapolate that model. For example, if we calibrate the model very accurately and we have a very tight fit, and then we use it for a different stage of the damage. For example, we calibrate this model and then we said, okay, I now consider that part of this building is broken and I use it for prediction, then those confidence intervals may be too tight because the error function bias will change for different stages. So if we want to use for extrapolation for a state of the structure that the data has not seen, and this is clearly outside of the realm of observation of the structure within the measurements, then it may be better to be on the conservative side and assume a zero mean, so the variances would compensate for that. The next considered structure is a footbridge on Tufts campus, which is referred to as Dowling Hall footbridge. So as I said, this bridge is on Tufts campus and goes through the different environmental conditions through the four seasons. Especially we have observed that below freezing points, the bridge behaves much stiffer than above freezing points. We have been continuously monitoring this bridge for the last couple of years. Here we use the data from beginning of 2010 to the end of 2012. That gave us 3 years of data. We measure 10 minutes of 5 minutes of data at the beginning of the hour, every hour, and get one set of modal parameters for every hour. So we have 8,721 sets of modal parameters during this period. We perform a hierarchical Bayesian model updating, and we update only one parameter. That's the effective stiffness of the deck. This plot shows the measured or identified natural frequencies for the first bending mode as a function of air temperature and as a function of the response magnitude. The left plot, you can see that there is a clear increase in the natural frequencies below the freezing point, and also there is another trend for above freezing point that still there is a decreasing trend. From this observation, we assume that, okay, the mean of my stiffness would have a trend which is green. It's represented by Q and S terms as a function of temperature, and a blue term which looks like an error function. And from the right plot, we also see that, oh, the frequency is also a function of the log of root mean square of response for any of the channels. Therefore, we have that in our equation for mu. Mu of theta gives me the expected value of the stiffness. So if I put the temperature and amplitude of excitation for every different values of temperature and the magnitude of excitation, I expect a different mean. This is what we can do at the hierarchical Bayesian updating. This is hierarchical level 2. In hierarchical level 1, I only update parameters of my stiffness, which are mu and sigma. In hierarchical level 2, I consider parameters for those mu and sigma. So I update the parameters of updating parameters, which are Q, S, R, Y, and tau, and sigma, of course, in the second equation. Here we can see a graphical representation of the hierarchical model updating. You can see all of the parameters that go into mu of theta and sigma of theta, and then from those we can get a distribution for our theta, and every observation of the modal parameters is one sample observation from theta basically. The hyperparameters are estimated through stochastic simulation. Here a Metropolis Hastings within Gibbs sampler is used. You can see the distribution of estimated parameters. You can see all of the parameters, hyperparameters, Q, S, R, epsilon, tau, Y, sigma, they have very tight distributions. So the uncertainty of those parameters are negligible, which is good, means we have enough data. Here we can see the estimated mu and sigma of theta as a function of temperature, for example, and excitation level. So if we consider the first level of hierarchical updating, which we only consider modal parameters, we do not use temperature measurements or amplitude of excitation, the mean would be constant. and the coefficient of variation, COV on the right plot, would have to be larger to compensate for that. However, if we consider the blue case, where we consider the temperature as well, you see the mean would change with temperature, and the coefficient of variation of the modeling parameters, theta, would drastically reduce. It goes from 12% to around 4%. Now, if we consider in addition to that, the amplitude of excitation, as you can see in the left plot in low, medium, high, in the right plot, you will have further reduction in the sigma, not significantly, by maybe from 4% you go to 3.7%, which is another substantial reduction when you want to consider your decision making. Okay, the calibrated model was eventually used for response prediction and damage identification, which I skipped that part and I show the response prediction in the previous application of the El Centro building in the next and final section of this presentation. Here I go back to the two-story building in El Centro and we perform hierarchical Bayesian model updating level 2, where we consider the effects of amplitude of excitation specifically. If you remember in the Dowling-Hall footbridge, temperature had the largest effect. In this building, amplitude of excitation has significant effect on the modeling parameters. These two plots show the identified natural frequencies for the first two modes of the El Centro building at different stages of damage and different levels of excitation. You can see at, for example, DS1, which is the focus of this study, the black dots vary a little bit, but the triangles and squares, which correspond to the shaker test, are significantly lower for both modes 1 and 2. And that is not permanent damage, because you can see we do ambient excitation, ambient excitation, ambient excitation, and then we do a shaker, it drops down, and then goes back up after that, and then it's at the same range, another drop when we do the shaker test, goes back up to where it was, until we have the permanent damage between damage state 1 and 2. So this variability is just caused by crack opening and closing without causing non-reversible damage. So we look at only damage state 1, and from the previous plot, we put the identified natural frequencies for modes 1 and 2 as a function of vibration level. So the previous plot is translated into vibration level versus frequency. And you can see the stars for forced vibration and circles for ambient. You can see close to vibration levels 0 for both modes, we have a cluster of circles which correspond to the ambient vibration levels because they seem to be negligible compared to forced excitations. And for the forced excitations, the frequencies are decreased drastically. And they seem to be following a linear trend. Based on this observation, we consider the stiffness mean for updating parameters follow a linear function as a function of vibration level, which is the root mean square of one acceleration in x direction and one in y direction divided by 2, as it's shown in the equation in the slide. This slide again summarizes the idea of deterministic versus Bayesian versus hierarchical Bayesian level 1, hierarchical Bayesian level 2 model updating. So both of them rely on measurements and the model, and the difference creates our either error function in the Bayesian case or residual. In the deterministic approach, we just find the optimal values by minimizing the difference. In a classical Bayesian, we also estimate the estimation uncertainty of the updating parameters. The hierarchical approach, however, we consider an underlying variability for updating parameters theta, and we estimate mu and sigma of those. In hierarchical level 2, we assume that mu and sigma follow a trend that is characterized by other parameters like parameters A and B here. So we do perform the hierarchical Bayesian model updating level 2 for this building, and the underlying updating parameters are assumed to follow normal distribution where the mean and covariance matrices are updated. The error function is assumed to be zero mean here with the covariance estimated, and parameters A and B are estimated as well. You can see that the model prediction, considering both error and variability of updating parameters compared to identified values of natural frequencies as a function of vibration level in this plot. Gray dots, gray circles are predictions, black dots are identified. We further want to use the model for prediction of time history responses, and here we use the model to predict time history response due to a sine sweep function, which is shown on top in the blue graph. This is the frequency versus time for the shaker. The shaker can output the shaker frequency, and this is measured from the shaker sensor. So we use that blue graph, use our model, and do the response prediction with confidence intervals. The pink shade is the 95% confidence interval for the time history prediction, which is obtained from a modal expansion. If we predict our modal parameters, they have confidence intervals. We perform a modal superposition and form the confidence interval of time history. You can see the prediction confidence intervals can be tight for certain sensors and not so tight for others, but overall it does a very good job. And here you can see a zoom in of the predictions. We have the actual measurements and we have the confidence interval predictions. And you can see at some instances there is a little bit of shift because the frequency changes in time for the actual measurements, but the model considers one amplitude of excitation in this prediction. However, the amplitudes are pretty accurate. Finally, I want to acknowledge the sources of support for this study and all the collaborators. This has been a collaborative project between many institutes and many people involved. So National Science Foundation, certain grants for traveling to Nepal, support at Tufts, NICE at UCLA for helping with testing the two buildings in upstate New York and El Centro, and the New York State Department of Transportation for making the upstate New York building available to us are acknowledged. The students involved for this presentation are my PhD students Mingming Song and Ashkan Akhlaqi, my former PhD student Iman Behmanish, and the current PhD students and former PhD students at University at Buffalo, Sina Yousefian Muqaddam and Supratik Bose. And I want to acknowledge my collaborators, Andrea Stavridis, assistant professor at University at Buffalo, Kostas Papadimitriou, professor at University of Thessaly, Greg Lombard, professor at KU Leuven, Andre Barbosa, associate professor at Oregon State University, and Richard Wood, assistant professor at University of Nebraska-Lincoln. Okay, I would like to thank you for your attention if you ended up watching the whole video. And if you have any questions, I would be happy to address. Just send me an email and mention that this is a question regarding the keynote of the EXA conference. Thank you very much.